Hello, greetings. So in this screencast, we're going to continue to work on our shortest route example, example 1. Only in this screencast, we will solve using LibreOffice Calc. So in terms of setting up our integer programming problem, have a look at the last screencast. So what I've done here to get things started is in LibreOffice, I've set up a table in which I created a row with our variables, right? So our routes. Then I called row 2 variable. And again, our variable is going to have values of 0 or 1. So for now, I just put in a value of 1. We'll have solve for that. And then I list the distance of each route. Okay. And what I want to do from here is, actually, let me rename this sheet part 1. Okay. What I want to do from here is set up our objective function, which will be true for all the cases, and then list out our constraints. Okay, so when we list out our constraints, we can type up cells for this, but it's not even necessary when working with Excel or LibreOffice Calc. We'll go through that. So basically, it's going to be setting up a cell for our objective function, and then setting up our node balances, our constraints 1 through 5. Okay, so I'm going to start by setting up my objective, okay, and it's going to be to minimize the distance between our starting city and final city. Okay, so our objective, it's going to be our distance in miles, okay, and it's going to be equal to, okay, it's going to be the sum of our variable times the distance in miles. So I can iterate over all of them, or I could use some product. Just for completeness, I'll do it. So it'd be this times this plus this times this plus this times this. Okay, so it's 285. Remember, another way to do this is some product, and I would just have, so say our distance row times our variable row. All right, will give us the same thing, 285. This is a little more concise and easier. Okay. All right, so now I'm going to add in my constraints. Okay, and these are essentially going to be our node balances. So I'll list out all 5. Okay, and I'll even list out, say this column's in, and the second column is out. Okay, so for problem 1, okay, I'm going to have 1 is equal to x12 plus x13. So 1 is going to be x12 plus x13. Okay, and again, 1 unit's going to be entering node 1. It can only exit via route 1, 2, or 1, 3. Right? So right now it's 2. But in order for this to hold, either 1, 2, or 1, 3 is going to have to be equal to 0. 1's going to have to be 1, and 1's going to be equal to 0. All right, so it'll work out in that we can only exit via one of those routes. Okay, so node 2, so 1, 2 plus 4, 2 is equal to 2, 3 plus 1. So it's going to be x12 plus x42. x12 plus 42 is x23 plus 1. Okay, 3, 2, 3 plus 1, 3. 2, 3 plus 1, 3. And that's going to be equal to 3, 4 plus 3, 5. 3, 4, 3, 4 plus 3, 5. Node 4, 3, 4. I need to get the 3, 4 is going to be equal to 4, 2 plus 4, 5. 4, 2 plus 4, 5. And for 5, I have 4, 5 plus 3, 5 4, 5 plus 3, 5. 4, 5 plus 3, 5. Oh, and I need to get the right variables. 4, 5 plus 3, 5 is going to be equal to 0. Okay. So now to solve, right, it's going to be, I'm going to go to solver. Okay. So I'm going to minimize this by changing the value of my variables. Okay. Then my constraints. Okay. So if I just do our generic constraints at first, okay, so our variables, okay, are all going to be less than or equal to 1. Okay. And then, I could do my variables are all integer, and I could also do my variables are all greater than or equal to 0 as well. Okay. Remember this greater than or equal to 0 or this integer in LibreOffice Calc I could get by assume variables are non-negative and assume variables are integer. This gives you a little more flexibility in that I could have just selected that some of the variables are integer, so you can handle mixed problems. So either case would be the same. Okay, so I'm going to minimize my objective function. So I have our general constraints, and then all of these are going to be qualities. If I want, I could do this as a group 2. I could do that, the variables in this column have to be equal to the variables in this column, or I could list them out all individually. Right? Either works. And so if I solve, right, it says that it successfully solved. Right, my shortest route is 55 miles. And so now we can look at this and try and check to make sure that our answer makes sense. Okay, so again, right, we could have solved this manually by hand just by iterating over the problem, but we're trying to set it up using integer programming to make it so that no matter how big or complicated the problem became, we could solve it just the same. So if I'm trying to go from city 1 to city 2, so again, my options would be I could directly go from 1 to 2, and that would be 100 miles. Or I could go from 1 to 3, and then from 3 I could go to 4, and then from 4 I could go to 2. Okay, so if I were to go directly from 1 to 2, that's 100 miles. If I were to go in this indirect route, that's 30, 40, that's 55. Okay, and so we know that the shortest route would be to go this way, right? 1, 3, 4, 2. Right? I can't go 1, 3, 5. I get stuck there. Right? So those are the only two routes, and so I could list out those two possibilities and say, hey, this is the shortest one. I get that. I know that. And solving, right? We see, x12 is 0. Okay, that means I'm not taking route 1, 2. Okay. x13 is 1, right? I'm taking route 1, 3. x23 is 0, I'm not going that way. x34 is 1, I'm taking route going from 1 to 3, then from 3 to 4. 35 is 0, and then 42 is 1, right? I'm going from 4 to 2 to get to my destination, and 45 is 0. I'm not going that route. All right, so we get, what we just found manually, that the optimal route is going to be to go from 1 to 3, then from 3 to 4, and then from 4 to 2, right? And that's going to give us a distance of 55 miles, and all of our constraints are solved. Okay, great. So again, this problem might seem a little simple. You might say, hey, I could just iterate over all these possibilities, but what we're trying to do is generalize this so that no matter how complicated the problem became, the solution strategy would be exactly the same. I could set it up exactly the same. I could solve just the same. All right. And now to tackle the next one, all I'm going to do is I'm going to copy my sheet. Okay, let's call it part 2. Okay, and so now what happens in part 2 is my balances are slightly going to change. All right, so and what we have is, we had a unit entering in constraint 1 in node 1 and exiting in node 2 here. In part 2, we're still entering in 1, but now we're exiting out of 5. So what's going to happen is constraint 1 will be the same. Okay, I'm not exiting out of 2, so I'll update that. And I'm instead exiting out of 5. Okay, so going from here to here, okay, 2, I get rid of that plus 1, and then I add it to 5. Okay, so now solving. Okay, so the nice thing is solver should pretty much keep everything in there, all right, and everything's going to be exactly the same. I just updated the constraints, and I get my result. Okay, so part 2 was what? So part 2, let's look at it and see if it makes sense. It was going from 1 to 5. So to go from 1 to 5, I could go 1, 3, 5, and that would be 90 miles. Or I could go, like, I can go 1, 2, 3, 4, 5, right? And this first trek is 100 miles. I know that's going to be greater than that 90, so that's not going to work. Or I could go 1, 3, 4, 5. That's 60 plus 30, that's 90 miles. And I think that's pretty much it, right? I could go 1, 3, 4, 2, but then I'm back at 3. It makes things cyclic. It's definitely not going to be optimal. So it should be 1, 3, 4, 5 for a total of 90 miles. So if we look at our solution, we find we should go from 1 to 3, then from 3 to 4, and 4 to 5. All right. So we find 1, 3, 3, 4, 4, 5 for a total of 90 miles. All right. So we get our solution. Okay. Cool. If we were to do part 3, okay, so all I'm going to do is copy our sheet. Okay, let's call this now part 3. Okay, bam. What's going to happen in part 3? Okay, so now we're going from 4 to 3. Okay, so constraint 1 is going to change. I'm no longer going to have anything entering. So constraint 1, left-hand side is going to be 0. Okay. So before node 5 had unit exiting, so that's no longer the case. So I go down here and update constraint 5, so that's 0. Now I have a unit entering in 3, or exiting in 3, and entering in 4. So for 3, I'm going to add 1 to the right-hand side. In 4, I'm going to add 1 to the left-hand side. Okay, and then everything else is the same. Since we've been working, just solve, keep result, get 35, and let's take a look at this. So to go from 4 to 3, how would we go from 4 to 3? So to go from 4 to 3, I could go, well, I can't go, if I go from 4 to 5, I'm stuck. I can't go from 4 to 3, so I have to go from 4 to 2, and then from 4 to 2, there's only one option. I can go from 2 to 3. So the optimal path is going, right, should be 4 to 2, then 2 to 3, and that should be a total of 35 miles. Okay, and that's exactly what I get. I get 4 to 2, 2 to 3, for a total of 35 miles. All right, so, that one would have been, trivial just looking at the problem. But again, what we're trying to do is we're trying to, systematically solve these problems so that no matter how complicated they could possibly become, the strategy is still exactly the same. All right, so this is a fictitious exercise of sending a single unit through our network, and so our objective function is to minimize the distance traveled, and so it's going to be, we'll have a binary variable, indicating whether or not we take a particular route times the distance of each route, and then where we get specific for, differentiating between parts 1 through 3 is in our constraints, our node balances, where that fictitious unit's entering and exiting. Okay, so hope that helps. These are nice problems because we could check looking at our picture and then also formally solve using integer programming and solver.